Okay, so today's lesson is on slope of the tangent formulae. One formula is for finding the slope of the tangent at a specific point, and the other formula is for finding the slope of the tangent at a general point. So our learning goals is that we're learning to find the slope of the tangent at a specific point using the slope of the tangent formula, also called the first principles formula. So when it says solve by first principles, it'll be the formula that you want to use there. And we're also learning to find the slope of the tangent at a general point using the derivative formula, which we're going to learn today as well. So what happened with Newton's method was mathematicians noticed that finding the slope of the tangent to a curve at a specific point always involved the same set of steps. You made your point Q a small distance h to the right of P. You found the slope of the secant, so the line joining P and Q. Then you took the limit as h approached 0 as the slope of the slope of the secant, and that gave you the slope of the tangent. So when mathematicians see the same procedure used again and again and again, they see if they can generalize it to a formula. So the formula they came up with for finding the slope of a tangent to a curve at a specific point, so at a curve, say y equals f of x, any curve, at a specific point, so that a value could be like 2 or 3 or 5, -2, whatever, and then you also want the value of the function at that a value. So the point xy, you can also think of this as a point xy, where x is a number and y is the corresponding y value, can be generalized to the following formula. So the slope of the tangent, so that's m standing for slope and then a subscript with the word tangent, is equal to the limit as h approaches 0 of the function at a plus h minus the function at a divided by h. So why is this the formula? So we have to remember back to yesterday. So first of all, this part here that I'm putting in this box represents the slope of the secant. So why does that represent the slope of the secant? So I'm just going to move back up a bit here because we've got some room over here. So the slope of the secant was always found by basically finding the change in y values over the change in x values. Okay, and you can think of the change in y values as the function, the value of the function at that number a, we're calling it, plus h. So that's y2 if you want. Subtracting y1, which would just be f at a. So that would be your y1. So y2 minus y1 over x2 would be a plus h. So that's our x2. Minus x1, which would just be a. So notice what happens here is we get our f at a plus h, whatever that turns out to be, and we subtract the number f at a. But in the bottom, if you do a plus h minus a, the a and the minus a subtract to give you 0, and you're just left with h on the bottom. So that's how this formula becomes the slope of the secant. And we talked about the procedure for finding the slope of the tangent as then, so we move back up here again, to find the slope of the tangent, you take the limit as h approaches 0 of the slope of the secant. And we just explained why that was the slope of the secant. So now all of a sudden we have this formula that we can use to find the slope of a tangent at a specific point, x equals a. So along with the formula, people, even mathematicians, they didn't like writing out m tangent every single time. It was kind of long for them to write out. So they developed some notation. So instead of writing slope of the tangent, they came up with a new notation, which is said. So if you were going to say this in your head or out loud, you would say f prime at a, f prime at a. So this little quotation mark is, we say prime in math, so f prime at a. But what it really means is we're finding the slope of the tangent when x equals a. but it's quicker to say f prime at a than slope of the tangent when x equals a. It also means that we start thinking of the slope of the tangent to a curve at a specific point as the derivative at a specific point. And we're going to talk more about this word derivative later on. But for now, I would like you to know is that slope of the tangent at a specific point A means the same thing as f prime at A. So then another version of this formula then, if you, rather than writing slope of the tangent here, which we could also write, so these things are all equal, the slope of the tangent is equal to f prime at A is equal to the limit as h approaches 0 of f at A plus h minus f at A over h. Okay, so we're going to try practicing a question that we could have done using Newton's method from yesterday, but we're going to instead do it with our new formula, okay? And hopefully shorten the procedure just a little bit. So the first question that you have to look at is use the formula to find the slope of the tangent to the curve y equals negative x squared plus 4x plus 1 at the point 3, 4. So you could think of the point 3, 4 as 3 being your a value and 4 being f at a. Meaning that if I were to substitute 3 in here, which I'll just show you really quickly, I should get 4 should be the corresponding y value. And you can see that it does end up being the corresponding y value. So, so here's a and here's f at a. So what was our formula again? So it says to find the slope of the tangent. So it was perfectly fine for us then to write down that m tangent is going to equal the limit as h approaches 0 of f at, and let's write the formula down the first time until we really start memorizing it. So f at a plus h minus f at a over h. But in our case, a is 3. So we could instead, and we could go straight to this step first if we wanted to. We could say the slope of the tangent to the curve y equals negative x squared plus 4x plus 1 at the point 3, 4 is going to be f at 3 plus h minus f at 3 over h. Okay? I know f at 3 is 4, which is great, but I don't know what f at 3 plus h is. So at this time, we're going to do some work on the side here to figure out what f at 3 plus h actually is. So I would now start over here, and I want to figure out what is this f at 3 plus h off to the side. So f at 3 plus h means I'm going to use this function I was given here and substitute, replace every x with 3 plus h. So if I do that, I get negative 3 plus h squared plus 4 times 3 plus h plus 1. And then I want to simplify that and make it as simple as possible. So I would need to use FOIL here. Here, just the distributive property. So plus 12 plus 4h plus 1. Here I would use FOIL. So I'd get 3 times 3 is 9, plus 3h, plus another 3h, plus h squared. Still plus 12 plus 4h plus 1. And then multiply through, so negative 9 minus 3h again, minus h squared, plus 12 plus 4h plus 1. And then collect like terms. So like with negative 9 is the positive 12, so that gives me 3. Plus 1 is 4. So those are used. So then I've got negative 3h minus 3h plus 4h. So that's going to be negative 2h. And then negative h squared. So So that's f at 3 plus h right there. So if I go back to my formula, I'm now ready to replace f at 3 plus h with 4 minus 2h minus h squared. And then there's a minus sign in the formula, minus f at 3, which we said was 4. We worked that out over here as well, all over h. So if you see here, f at a plus h, we replaced with 4 minus 2h minus h squared. And then f at a, we were able to replace with 4. So then if we simplify the numerator by collecting like terms, we've got this 4 and this minus 4, which give us 0. So we're left with negative 2h minus h squared in the numerator and h in the denominator. So we could divide top and bottom by h, or we can common factor h out of the numerator. So if I common factor h out, because I want to get rid of this h, because I can't let h approach 0 if I've got h in the denominator also approaching 0, because division by 0 is impossible. So if I can factor out an h in the top that will divide out with the h in the bottom, I'll be in good shape here. So I get negative 2 minus h over h. And then h divided by h is 1. So now I've gone to the fact that the slope of the tangent, so that comes all the way down here, is equal to the limit as h approaches 0 of negative 2 minus h. And now our denominator is 1. So now we're free to let h approach 0 because that doesn't blow up our function because we're not letting the denominator approach 0 anymore. So if we let h approach 0, the limit as h approaches 0 of negative 2 minus h is just going to be negative 2. So we've just showed that the slope of the tangent to that curve, y equals negative x squared plus 4x plus 1 at the point 3, 4, is negative 2. And so we've answered that question. So we could just put a little therefore in front, box up our answer, done. Okay, another question. So given f at x is the square root of 2x minus 1, find f prime at 13 and explain its meaning. So we talked earlier that f prime at 13 means find the slope of the tangent to the curve when x is equal to 13. Okay, so when our x value is equal to 13, we need the slope of the tangent. So let's start off with the formula. Instead of m tangent, we'll start off with our f prime at a formula, but obviously we see that a is equal to 13 in this case, is equal to the limit as h approaches 0 of f at a plus h minus f at a over h. But we're really finding f prime at 13, which is equal to the limit as h approaches 0 of f at 13 plus h minus f at 13. So all we're doing is replacing a with 13 over h. So f prime at 13 is equal to the limit as h approaches 0 of, well, I want to replace f at 13 plus h with something that I know that it is. So we'll go to the side again here, and to find f at 13 plus h, we'll replace x with 13 plus h. So that's going to be the square root of 2 times 13 plus h minus 1, which is the square root of, distribute there, 26 plus 2h minus 1, and then we can collect the 26 and the minus 1, so it's the square root of 25 plus 2h. So now we can replace f at 13 plus h here with the square root of 25 plus 2h. We also need to know what f at 13 is, so that we can also figure out. So f at 13, maybe I'll come back up here and do that. So f at 13 is equal to the square root of 2 times 13 minus 1, or the square root of 26 minus 1, or the square root of 25, which is nice because that ends up being 5. Okay, so we can replace f at 13 with 5 over h. So again, we have that correspondence where we've got f at 13 plus h, but then we figured out what that was off to the side, and then we could replace it with the square root of 25 plus 2h, minus, from the formula, f at 13, which we also found up here. F at 13 turned out to be 5 over h. So again, if we could let h approach 0 now, but we can't because then our denominator approaches 0. And if the denominator approaches 0, then we're pretty much dividing by 0, which is impossible. So we can't do that. And the h that we want to kind of divide out with is trapped under the square root sign. So that's where we use multiplying by the conjugate, top and bottom by the conjugate radical. So we're multiplying by 1 in a way that helps us out of the trap. So what I want to do is multiply the numerator by the square root of 25 plus 2h plus 5. So it's called a conjugate radical because it's exactly the same except for the sign in the middle. So minus here, plus here. Okay, but whatever I multiply the top by, I also have to multiply the bottom by that. So that really, I am just multiplying by 1, which doesn't change the value at all. So I'm going to multiply the bottom by exactly that same thing. So why is multiplying by the conjugate such an important strategy? Well, the reason is because it frees that h from underneath the square root sign, as you'll see in a second. So we're going to think of this as doing FOIL. So this times this in the numerator. So when you do FOIL, you multiply the first by the first. So when you multiply the square root of something by the square root of the exact same thing, you get the square root of that squared. Okay, and what squared does is it undoes square root. So root of 25 plus 2h multiplied by itself just gives you 25 plus 2h, and all of a sudden that square root is gone. But we also have to then multiply root of 25 plus 2h by positive 5. So that's going to give us plus 5 root of 25 plus 2h. So now we've done the firsts, we've multiplied the firsts together and the outsides together. So now we're going to multiply the insides together in FOIL. So that's going to give us negative 5 root 25 plus 2h. And then the last, finally, negative 5 times positive 5 is negative 25. So that's the numerator expanded. And we're expanding the numerator because we're really hoping we're going to end up with an h that can divide out with this h that when approaching 0 is going to blow up our function. So we don't want that. So we're not going to expand the denominator. We're just going to leave our h where it is and say we're multiplying it by the denominator root 25 plus 2h plus 5 not under the square root there. So we're just going to leave it in that format. So why is multiplying by the conjugate so great? Well, the reason is because we're multiplying by the conjugate, so exactly the same thing except for the signs are different. These two terms here end up always adding up to 0. So plus 5 root 25 plus 2h minus 5 root 25 plus 2h adds up to 0. So those terms add up to 0 and are gone. So our numerator becomes f prime at 13 is the limit as h approaches 0. So if those terms are gone, we just have 25 plus 2h minus 25. And you can already see what's going to happen there. So all of a sudden the 25 minus 25 add up to 0. So we've got f prime at 13 is the limit as h approaches 0 of 2h over h times root of 25 plus 2h plus 5. And now these h's, so this is 2 times h and h times this thing, we can divide out those h's, which is great because that's our problematic h there that we wanted to divide out in the denominator there. Because now if we look at what we're taking the limit of, it's safe to let h approach 0. So we can actually find the slope of the tangent. So my next step, I'm actually going to let h approach 0. So as I let h approach 0, it doesn't affect the numerator because the numerator is not in terms of h. And then the denominator, as h approaches 0, 2 times h will also approach 0 because 2 times 0 is 0. So we end up with, in the denominator, root 25 plus 5. So f prime at 13 is 2 over, so that's going to be 5 plus 5 is 10, which reduces to 1/5. So the question said, given f at x is the square root of 2x minus 1, find f prime at 13 and explain its meaning. So we found f prime at 13, but we need to explain its meaning. So what does this mean? Well, f prime at 13 means the slope of the tangent at the point where x is 13. So we just determined that the slope of the tangent to the curve f at x equals the square root of 2x minus 1 at the point where x is equal to 13. So the slope of the tangent to that curve when x is 13 is 1/5. And so we've found it and explained its meaning. So that's our second problem. Here's our third problem. So it says find the equation of the tangent line. So again, this we add steps on here. So not only do we have to find the slope of the tangent, when they ask you to find the equation of the tangent line, once you have the slope found, you need to then go ahead and find the equation of the tangent line. And we want the equation of the tangent line to the curve f at x equals 3 over 5 minus x, which they've drawn here on a graph for us at the point p 1/3. So here's my a and my f at a again. And let's kind of see where that point is. So when x is 1, y is 3/4. So we want the slope of the tangent right at this point. So we can see if we were going to draw a tangent in, it would be positive sloping, but a fairly low slope we would expect. And we actually want to find the equation of that tangent line that we would draw in. And they also want it in standard or scalar form, so we could have a little vectors application in here as well. So we're going to start off saying that we want the slope of the tangent. And we know that's going to be the limit as h approaches 0 because I'm using the first principles formula here. Of f at a plus h minus f at a over h. But we've determined that a is 1. So that's going to be the limit as h approaches 0 of f at 1 plus h minus f at 1 over h. So now I need to know what f at 1 plus h is. So I'm going to come over here, replace x with 1 plus h. So I get 3 over 5 minus, careful here, 1 plus h in brackets. That minus is going to distribute. So I get 3 over 5 minus 1 minus h, or 3 over 4 minus h. So I've got the limit as h approaches 0 of 3 over 4 minus h minus f at 1, which was 3/4, all over h. So I've got this 3-layer fraction that I have to simplify. So when you have this big fraction bar here, it means you have to simplify the numerator and denominator as much as possible before you can divide. So in the numerator, I am subtracting fractions. And hopefully we've done math long enough here that we remember to subtract fractions, you need a common denominator. And to get a common denominator, you multiply. So it's going to be 4 times 4 minus h. And I'm just going to leave them multiplying each other rather than multiply it through. It's also easier to see, okay, so what did I have to multiply the bottom of this fraction here by? 4. So I'm going to multiply the top by 4. And what did I have to multiply the denominator here by? 4 minus h. So I'm going to multiply the top by 4 minus h. But that's still, and often this part gets forgotten, all divided by h. So people get so caught up in simplifying the numerator because it involves fractions that they forget about the denominator. And the denominator of h is our trap that we're trying to get out of anyways. So we do want to end up being able to divide out that h somehow. So our next step is going to be to have one just denominator in the numerator now, which is 4 times 4 minus h. And then in this case, it's a subtraction, 12 minus 3 times 4 minus h, all over h. So now I'm going to expand here to simplify the numerator of the fraction in the numerator. So I get 12 minus 12 plus 3h. Careful with that sign. That's going to depend on whether your answer makes sense to you or not. Over 4 times 4 minus h. And then dividing by h. So dividing a fraction by h is the same as multiplying that fraction by 1 over h. So if I want, I could do that at this time. And then I'm going to continue to simplify here as I go along. So I've got 12 minus 12 is 0. Nice. So I'm just left with 3h over. Now this denominator here is multiplying this denominator here because those fractions are multiplying there. So I've got 4 times 4 minus h times h. So a nicer way to write that would probably be 4h times 4 minus h. So now, and the numerator I'd been multiplying by 1, so it didn't change from 3h. So now this problematic h here can divide with that h on top. I have 3 times h on top and 4 times h times 4 minus h on the bottom. So these h's can divide out. So now I've got the limit as h approaches 0 of 3 over 4 times 4 minus h. Now let's see if it's safe to let h approach 0. It doesn't matter about the numerator. In the denominator, if I let h approach 0, I'm going to have 4 times 4. So no problem there. So I'm going to actually take the limit now. And that's when I don't write it anymore once I've taken it. So I'm letting h approach 0. So I'm going to have 3 over 4 times 4. Or meaning that the slope of the tangent, the slope of the tangent is going to be 3/16. So 3/16. Let's go back to our picture here for a second. And I didn't set up here with a ruler, so I'll try to draw it in as best I can. But we would want to draw like a tangent line in and only touch in that one point there. And it does look like it has a non-steep slope, but it is positive, so 3/16 makes sense. But we actually want the equation of this tangent line. So that's going to be like the next part of our question here, is finding the equation of that tangent line. So what do we know about it? We just found out that its slope of this tangent line here was 3/16. Now, because we want the equation in standard or scalar form, it might be smart of us to convert that slope into a direction if we are good enough at remembering that. So the direction vector of that line would actually be, because this is change in y over change in x, so 16, 3. which means that the normal to the line, which we know we need for standard or scalar form, would be 3, negative 16. So now all of a sudden, I know that in scalar form, it's ax plus by plus c equals 0, where the normal to the line is the a coefficient and the b coefficient, which I just determined here. So far I know that the equation of the tangent line in standard form is going to be 3x minus 16y plus a constant c equals 0. But I also know from my picture up here and from them giving me that this point is on the line. It satisfies the equation of the line. And that point was the point 1 3/4. So that means if I put 1 in for x and 3/4 in for y, my equation should be balanced because that point satisfies the line. And so if we substitute it in an x and a y, c will be our only unknown. And it's going to work out nice even with the fraction here. So 3 minus 12 that turns out to be, plus c equals 0. So 16 times 3 is 48, divided by 4 is 12. So we're going to get 3 minus 12, which is negative 9, plus c equals 0. Or we get that the constant c is 9. So therefore, now we can write our statement then. The equation of the tangent line is, so in standard form, 3x minus 16y plus 9 equals 0. All right, so we used a little bit of vectors there. You could have also alternatively first found the equation of the tangent line in slope-intercept form and then changed it into standard form. This way is just a little more direct and takes fewer steps. But it would be totally okay if you wanted to first find it in slope-intercept form and then change it to standard form by multiplying to get rid of the fraction. And remember, you always have to make sure that the number in front of x is a positive whole number. It has to be positive, just like it did in vectors, whole number. Okay. So that's kind of the end of the first part of the note where we're finding the slope of the tangent at a specific point. And that was kind of the evolution of calculus. So first there was Newton's method where mathematicians realized you're always doing the same 3 steps. You were finding a point close to a point Q close to P that was h away. Then you were finding the slope of the secant. Then you were finding the slope of the tangent by taking the limit as h approaches 0 of the slope of the secant. Then they developed that into a formula for finding the slope of the tangent at a point. So then we're going to see what happened next. So next, mathematicians ask the question, what if we wanted to find the slope of the tangent at the places where x equals 1, x equals 2, x equals 3? What if we wanted to find it everywhere, all for the same function? Do you really have to use that first principles formula 4 different times, or if you wanted to know it 10 places 10 different times? Or can I find a general formula for the slope of the tangent to that specific curve at a general point? And that general point would be at x and then f at x, which is x squared minus 4x minus 3. And the answer is yes. So the formula is called the derivative function and requires us to use different notation to express the slope of a tangent. So we never write out all the words slope of the tangent at a general point, okay? Instead, we write f prime at x, and f prime at x means the derivative. The derivative of the function at x as well. So you'll hear that word derivative. The slope of a tangent to a function y equals f at x at a general point, x f at x, is also called the derivative of f at x with respect to x and is given by this formula. So how is this formula different from the one that we were just using? So instead of being f prime at a, so at a specific number, we're now finding it in terms of x. Okay, so the algebra is a little more intense, but once you've found it in terms of x, you can then go and find it at any number very quickly and easily. So we're going to start off with this question. So the picture they have drawn here is the graph of y equals x squared minus 4x minus 3. And we're going to find an expression that represents the slope of the tangent anywhere on that curve. Okay, so we've got our formula. So the first thing we would need to know before we use the formula would be f at x plus h. So we gotta actually go about finding that. So f at x plus h. So I'm going to use the definition of the function over here. So I'm going to replace x with x plus h, and that's squared, minus 4 times x plus h, minus 3. And now I'm going to expand and simplify that. And then I'll know what f at x plus h is, and I can start to use the formula. So x plus h squared, if you can expand a binomial in your head, it's going to really help you out in this unit of calculus. So practice doing that, but always check until you're 100% confident that you can do it. So for instance, I know that's going to give me x squared plus 2xh plus h squared, but until you are able to do that, you're going to write out all the terms from the FOIL and then collect like terms, which there's only the 2xh here, and everything else is not like at all here. Okay, so that's f at x plus h. So now I'm going to go to my formula that says that f prime at x is equal to, so f at x plus h minus f at x. Oh, I did the worst thing I could do. Forgot the limit as h approaches 0. Do not forget that. That is the whole calculus part of the question, is that it involves the limit as h approaches 0. Okay? Otherwise, you're just finding the slope of the secant, which is not finding the slope of the tangent, which is not calculus. So please don't forget to write that in like I just did. Concentrate while you're doing the question. All right, so then the limit as h approaches 0 of, so f at x plus h, we just found that out here. And it's not nice. It's got a lot of terms there, but we can replace f at x plus h with x squared plus 2xh plus h squared minus 4x minus 4h minus 3. Then there's a subtract in the formula. So subtract f at x. F at x has got 3 terms in it. X squared minus 4x minus 3 all over h. So that's going to equal the limit as h approaches 0 of x squared plus 2xh plus h squared minus 4x minus 4h minus 3. Now distribute that negative through the bracket, and you're going to get minus x squared plus 4x, because you've got a negative times a negative, and then another negative times a negative, so plus 3 all over h. See if there's any like terms in the numerator now. So we've got an x squared and a minus x squared, so they add up to 0. 2xh, nothing else ending in 2xh. H squared, no other h squared term. Minus 4x plus 4x, so those add up to 0 again. Minus 4h, not another term, just ending in plain h. Minus 3 plus 3 is 0. Minus 3 plus 3 is 0. So you'll notice that these 3 terms, so when we subtracted f at x, they all made 0 pairs with 3 of the terms in our f at x plus h squared part. And why that's so great is because every term left in the numerator now contains an h, and I can common factor that h out so that it will divide out with that problematic h that's in the bottom. So f prime at x is now coming down to the limit as h approaches 0 of, so if I common factor an h out of the numerator, I would mentally divide each of these terms by h. I've got 2x plus h minus 4 over h. And now I've got h times and divided by h in the same question. Those can divide out. And now I've got the limit as h approaches 0 of 2x plus h minus 4. So now my denominator is 1, and I can let h approach 0. So I'm ending up getting that f prime at x is equal to 2x, because that's not affected by h approaching 0, plus 0 minus 4. So f prime at x is equal to 2x minus 4. So then this question asks me, like, can I find the slope of the tangent at 1? So when x is 1, that's where my point would be right here. If I was drawing a tangent in, I would expect it to be negative, okay? And, well, a lot steeper than the last tangent that we drew in. So for instance, if I want to find the slope of the tangent at 1, that's the same thing as finding f prime at 1, which gives me negative 2. So that means that the slope of the tangent at this point would be negative 2. So that means if I know this point and I want to draw in more points on the tangent line and the slope's negative 2, I would go down 2 over 1, and then in this way up 2 over 1, up 2 over 1 again, up 2 over 1 again, up 2 over 1 again. And then if I drew that incorrectly, I can see that that does definitely look like the slope of the tangent when x equals 1. How about when x equals 2? Well, that would be f prime at 2. So first let's look on here when x is 2, oh, right at the bottom there. So I would be suspecting a horizontal tangent, but let's see what happens. So it's going to be, again, 2x minus 4, so 2 times 2 minus 4 is 0. Makes sense that the tangent to this point right at the bottom of the parabola would be 0. Perfect. So you should have a blank page coming next, so you could keep going with this if you wanted. So when x equals 3, f prime at 3. Now I'm going to look back at my picture here and do a little guesstimate. So when x is 1, 2, 3, my point is down here. So it's going to have a positive slope and it's symmetrical. So I would expect it to be positive 2 because it's right opposite 1. Where the slope ended up being negative 2. So let's see though. F prime at 3 again. So we're going to have f prime at 3 being 2 times 3 minus 4, 6 minus 4, which is 2. Makes sense. If we look at our picture, so the tangent here has a slope of positive 2, so up 2 over 1, up 2 over 1, up 2 over 1, and then we could draw our tangent in here. So far this derivative function is working out great for us. We found the slope of the tangent at 1, 2, 3, and then they want us to find it at 4. So let's go back here. When x is 4, f prime at 4 is going to be 2 times 4 minus 4, or 8 minus 4, or 4. So that means when x is 4, my picture here, so 1, 2, 3, 4, there's my point. And the slope of the tangent is 4, which means up 4 over 1. Up 1, 2, 3, 4 over 1. Ran out of room there. Over 1 this way down, 1, 2, 3, 4. So steeper slope, it looks like it should be a steeper slope. And we've drawn in all our tangents for 1, 2, 3, and 4 here. So that's how the derivative is important. It allows you to find the slope of the tangent anywhere, not just at one specific point. So we're going to go on to another example of where we are going to find the derivative first, or f prime at x, or the slope of the tangent anywhere. They all mean the same thing. And then apply it to finding the slope of the tangent at a specific point after. So this time we're given f at x is the square root of 2x minus 3, and we're asked to find f prime at x. So again, I'm going to start off writing down the formula to help us remember it. So the formula for f prime at x is it's the limit as h approaches 0 of f at x plus h minus f at x over h. And then before we can substitute in, we need to know what is f at x plus h. So I'm going to find that off to the side here. So f at x plus h is the root of 2 times x plus h minus 3, which is the root of 2x plus 2h minus 3, which doesn't simplify any more than that. And we already know f at x is the root of 2x minus 3. So now we can substitute. So the limit as h approaches 0 of the root of 2x plus 2h minus 3 minus f at x, which was the root of 2x minus 3 over h. So a reminder of that correspondence again. This is f at x plus h, and this is also f at x plus h that we found by subbing x plus h in for x. Here's f at x, which was defined for us, and here it is in our formula. And then the minus sign is in the formula itself, carries down. All right, so we've got this h. We can't let h approach 0 because then the denominator would approach 0. So there's got to be something to do. And usually when you see square roots, you think of multiplying by the conjugate radical, top and bottom. So that is what we're going to do. But we've got two square root signs here, so the conjugate radical still works the same way. It's going to be root of 2x plus 2h minus 3. Instead of a minus, plus, so exactly the same except for the sign, the root of 2x minus 3. And then whatever we do to the top, we have to do to the bottom. So we're going to multiply the bottom by exactly the same conjugate radical. And then we're going to do this FOIL. So we're going to multiply this whole numerator by this whole numerator using FOIL. So first times first. These are exactly the same. So it's going to be the square root of this squared. So it's going to free 2x plus 2h minus 3 from the square root, because squaring undoes that square root. So that's the firsts multiplied together. Now we're going to do the outers. So they're two different roots, so they just have to stay looking like that. So it's going to be plus root of 2x plus 2h minus 3, root of 2x minus 3. So we've done the first and the outers. So now we're going to do the inners. So that's minus root of 2x minus 3, root of 2x plus 2h minus 3. And then the lasts. Now they're the same again, roots, except for we're multiplying a negative times a positive. So that's going to give us a negative, but we're going to undo the square root because we're multiplying two squares by themselves. This bracket here, though, so important. Subtract 2x minus 3, because a negative times a positive is a negative. You don't just happen to subtract whatever comes first, the 2x. You've got to think you're subtracting whatever was under that square root sign. So that's all over h. So we see here, we've got this yucky term. So this big, huge plus those two roots multiplying together, but then we've got minus those two square roots multiplying together. So they add up to 0, which is really nice for us. So they add to 0 and they're gone. So we've got 2x plus 2h minus 3. And then if we distribute that minus there, we've got minus 2x plus 3 all over h. Oh, I forgot to multiply the denominator. That's another common mistake that I made. So top by top we did, but it's also bottom by bottom, but we just leave it without doing the FOIL. So we just leave it h times root of 2x plus 2h minus 3 plus root of 2x minus 3. Okay, so now we're correct. We multiplied the top by the conjugate, and that gave us this FOIL thing. We multiplied the bottoms together, the denominators, and we just left it as h times this in brackets. So now, and then we simplified the numerator a little bit. We're going to simplify it some more. So we've got the limit as h approaches 0 of, okay, so 2x, is it, they're a like term? Yes, minus 2x, and they happen to be opposites, so they add to 0. 2h, nothing like with 2h, and then minus 3 plus 3 also add up to 0. So the whole numerator just breaks down to just 2h. So that's why multiplying by the conjugate radical on the top and the bottom is so powerful, because we start off with this really complicated numerator and we can break it down just into 2h. And then in the denominator we have our h still times this yucky root of 2x plus 2h minus 3 plus root of 2x minus 3. But now I have 2 times h on the top and h times something on the bottom. I can divide out those h's. So that problematic h that was not allowing me to let h approach 0 is now been divided out. So my numerator now is just 2, and my denominator now is root of 2x plus 2h minus 3 plus the root of 2x minus 3. Okay, so now I'm ready to let h approach 0. So if I let h approach 0, the numerator stays as 2. The denominator is going to become, so the h approaching 0 doesn't affect 2x, but as h approaches 0, 2h. 2 times h approaches 0 as well, so I'm just left with 2x minus 3 here, plus another 2x minus 3. So then you kind of notice that these two terms are exactly the same. Root of 2x minus 3 plus root of 2x minus 3. There's 2 of them. So we've got 2 over 2 root 2x minus 3's. So these 2's divide out, leaving you with a 1 in the numerator. So we found the derivative, and it ends up being actually pretty nice. So f prime at x, the slope of the tangent to the curve anywhere, ends up being 1 over the square root of 2x minus 3. Interesting relationship, since f at x, way back at the start of the question, was the square root of 2x minus 3, and the derivative ended up being 1 over the square root of 2x minus 3. And then part B, now they want us to find f prime at 2. So that's just going to be 1 over the square root of 2 times 2 minus 3, which is 1 over the square root of 4 minus 3, which is 1 over the square root of 1, which is just 1. Okay, which means that the slope of the tangent to that curve when x is 2 would be 1. That's what it means. Okay, so there's another question where we first found f prime at x, so the general derivative or the derivative anywhere, and we had to multiply by the conjugate, numerator and denominator, to get it. And then once we found the derivative f prime at x, we were asked to find the slope of the tangent at a specific point 2. We just substituted in to our derivative formula that we made and ended up getting the slope of the tangent to be 1. Okay, last question. So this says if y is equal to 1 over 5x minus 1. Part A says find the derivative of the function. Part B says find the derivative at the point when x is 2/5. So we can see x is 2/5 is, so here's half, it's before half, so up here somewhere. So it's going to be a pretty steep negative slope, it would look like to me, but we'll see. So first we want to find the derivative though, so we need our derivative formula. So our derivative formula is that f prime at x is equal to the limit as h approaches 0 of f at x plus h minus f at x over h. So then I want to know what is f at x plus h. So I'll find that out off to the side here by replacing x with x plus h. So f at x plus h is going to turn out to be 1 over 5x plus 5h minus 1. So now we can substitute. So it's going to be the limit as h approaches 0 of 1 over 5x plus 5h minus 1 minus f at x, which we haven't figured out yet, so I'm going to go down here to do that. So, oh sorry, f at x is given to us, my bad. So f at x is 1 over 5x minus 1 all over h. So again, we've got this 3-layer fraction where we have to get a common denominator in the numerator. And because we're finding f prime at x, usually makes the algebra a little bit more tricky. So our common denominator is found by multiplying the two denominators together. So I'm going to have the common denominator be 5x plus 5h minus 1 times 5x minus 1. 5x plus 5h minus 1 times 5x minus 1. And then that's all over h, don't forget that. So in the first case, I had to multiply the numerator by 5x minus 1. And in the second case, I had to multiply, the denominator by 5x minus 1, so I have to do that to the numerator. Second fraction, I had to multiply the denominator by 5x plus 5h minus 1. So I have to do that to the numerator as well. So f prime at x is equal to the limit as h approaches 0 of, so now I'm just going to have my one common denominator. And I'm going to subtract the numerator. So that's 5x minus 1 minus 5x plus 5h minus 1 in brackets. So that minus sign is going to distribute. So important that you remember that all over h. So f prime at x is the limit as h approaches 0 of 5x minus 1 minus 5x minus 5h plus 1 over 5x plus 5h minus 1 times 5x minus 1, and then divided by, which means multiply by the reciprocal, 1 over h. Okay, so let's look at the numerator here. I'm multiplying by 1, which isn't going to affect anything, but 5x minus 5x is 0. Negative 1 plus 1 is 0, so the numerator is just left as negative 5h over this h here, which I'm going to bump out front here, a monomial term, times this trinomial term, times this binomial term. And it's this problematic h that we want to divide out, and we're now able to do that. So those h's divide out. So now we've got f prime at x equal to the limit as h approaches 0 of negative 5 over 5x plus 5h minus 1 times 5x minus 1. So now it's safe to let h approach 0. And we're going to end up with, so if we let h approach 0, negative 5, the numerator stays the same. The denominator, 5x isn't affected, but plus 5h, that's going to become plus 5 times about 0, so that's going to go to 0, minus 1, times another 5x minus 1, which can be written more nicely as f prime at x is going to be negative 5 over 5x minus 1 all squared. Okay, so there's our f prime at x, so that's part A, finding the derivative. B says find the derivative at the point where x equals 2/5. So now they want us to find for part B, f prime at 2/5. So that's going to be negative 5 over 5 times 2/5. So replace x with 2/5 minus 1 squared. Or negative 5 over, so 5 times 2/5 is 10/5 or 2 minus 1 squared. So that's going to become negative 5 over 1, which is just negative 5. Remember, we predicted that the slope would be negative and steep. So negative 5 is pretty steep and it's negative. So it makes sense that if we were drawing in a tangent line here, well, we can even, well, we're just guesstimating that anyways. But if we drew in our tangent line, guesstimating, it would look something like this. That does look like it would have a slope of approximately negative 5, which is what we got. All right, so we learned a lot today. Our success criteria. We can use the formula, the slope of the tangent formula, first principles formula. The limit as h approaches 0 of f at a plus h minus f at a over h to find the slope of the tangent to a curve at a specific point a f at a from first principles. I can find f prime at a, and you know what it means. You know what it means to find the slope of the tangent at that specific point. We know what f prime at a means. That means the slope of the tangent when x is a. We can find the equation of the tangent line to a curve at a specific point in both slope-intercept form, so y equals mx plus b, or standard form. We know what it means to find the derivative of a function, so that's the slope of the tangent anywhere. So it's a general formula for the slope of the tangent to that function at any point. And we can use the derivative formula to find the slope of a tangent at a general point, and then use it to find the slope of a tangent at a specific point that you're given later. Okay,